Something out there is expanding the universe faster than physics says it should be able to. Not slightly faster, catastrophically faster. And the closer scientists look, the worse the numbers get. But before we get there, we need to start with something that was supposed to be routine, a measurement so standard that no one expected it to break cosmology. Alright, let's go. Number 10. The universe's impossible baby galaxies. In February 2023, Erica Nelson at the University of Colorado, alongside a team of researchers, published results from the James Webb Space Telescope that stopped the cosmology community in its tracks. They had spotted 6 massive galaxies, enormous, fully formed structures, existing just 500 to 700 million years after the Big Bang. That's barely a cosmic blink. For context, our own Milky Way took billions of years to reach its current scale. These galaxies shouldn't be there, not in any meaningful way that our models can absorb. The standard cosmological model, the Lambda CDM model, the one we've spent decades fine-tuning, predicts that the early universe was a smooth, hot soup of particles slowly. Clumping under gravity, big galaxies form late. That is the rule. But Nelson's team found galaxies with the stellar mass of our own Milky Way, sitting in an infant universe that hadn't had nearly enough time to build them. Nelson herself said it directly: if even one of these galaxies is real, it will push against the limits of our understanding of cosmology. And these weren't fuzzy detections. They were clear, bright, unmistakably there. The part that should concern you is this: since that initial detection, more of them have been found. Not fewer. More. As of 2025, researchers at the University of Missouri identified 300 unusual early galaxy candidates from JWEST data, each one compounding the same impossible pattern. The question this raises doesn't have an answer yet. Where did all this mass come from, so fast, so early, and why doesn't our best model of the universe have room for it? That question connects directly to something we'll reach in number 3, something that makes the galaxy problem look almost manageable. Number 9. The Hubble tension. In 2019, Adam Rees at Johns Hopkins University, the same Nobel Prize winning astrophysicist whose team helped discover that the universe is accelerating, completed what was then the most precise measurement of the universe's expansion rate ever made. He got a number, approximately 73 kilometers per second per megaparsec, meaning for every 3.26 million light years you look outward, space is flying apart 73 kilometers every second faster. The problem is the other number. When cosmologists calculate the expansion rate using measurements of the early universe, specifically the cosmic microwave background, the ancient light from 380,000 years, after the Big Bang, they get 67, not 73. 67, that's a nearly 10% discrepancy, and at the precision levels these teams are working, 10% is not a rounding error. It's a crisis. Here's where it gets disturbing. Both measurements have now been independently verified using entirely different instruments and methods. In 2024, Wendy Friedman at the University of Chicago published her own JWEST-based measurements, and Adam Rees published his. They disagreed with each other, and both disagreed with the early universe value. The universe is apparently expanding at a rate that depends on how you measure it. 3 different answers. One universe. No reconciliation in sight. What no one talks about is what this actually means. If the tension is real, it means there is something in the fabric of space-time between the early universe and today that we have not discovered yet. Some ingredient, some force, some unknown physics quietly operating across 13 billion years, hiding in the gap between 2 numbers. And that missing ingredient connects to something in number 4 that should fundamentally disturb you. Number 8. Fast radio bursts. In 2007, Duncan Lorimer at West Virginia University was reviewing archival radio telescope data when he found something extraordinary. A burst of radio energy so intense it had briefly outshone the entire galaxy it came from, lasting less than 5 milliseconds, gone before anyone could react. The signal had traveled so far that it had been dispersed by the intergalactic medium, telling scientists it came from cosmological distances, billions of light years away. Today, we know these are called fast radio bursts, and we've detected thousands of them. Some repeat, some don't. Some come from known objects like magnetars, extreme neutron stars with incomprehensible magnetic fields. But in January 2025, researchers at UC Berkeley published findings on a burst-designated FIRB 2240209A, detected in February 2024, and it didn't fit. It came from a location associated with an old, dead stellar population, a place where the type of star thought to produce these bursts simply does not live. The math says something is generating these events that we haven't identified. Each burst releases more energy in a single millisecond than our sun produces in 3 days. And still, after nearly 2 decades of study, a significant fraction of them point to source environments that match no known astrophysical model. The real implication is far worse than the mystery itself. If something is producing energies this extreme in environments this unexpected, our catalog of what exists in this universe is incomplete in ways we cannot yet quantify. Number 7. The cosmic axis of evil. When NASA's MAP satellite mapped the cosmic microwave background in extraordinary detail in the early 2000s, researchers expected to find a random, statistically uniform patchwork of temperature fluctuations, ancient ripples from the infant universe, scattered in every direction with no preference for any particular axis. They found something else entirely. The largest temperature patterns in the CMB, the quadrupole and octupole moments, structures spanning billions of light years, were aligned, not randomly, aligned with each other, and disturbingly, aligned with the plane of our own solar system and with the trajectory of Earth's orbit around the Sun. Cosmologist Kate Land at Oxford named it the Axis of Evil in a 2005 paper, and the name stuck because the implications were genuinely unsettling. In a universe born from quantum randomness and evolved under the influence of forces operating equally in all directions, there should be no special alignment. There should be no preferred axis. The universe is supposed to be isotropic, the same in every direction. But it isn't. And here's what no model has convincingly explained in the 20 years since. Why does the largest scale structure in the observable universe seem to know about the orbital plane of a tiny planet around an unremarkable star in an ordinary galaxy? The coincidence is either a measurement artifact that has survived every attempt to eliminate it, or it is evidence of something deeply wrong with our assumptions about our own. Place in the cosmos. Number 6. Dark matter that no one can find. In the 1970s, Vera Rubin at the Carnegie Institution of Washington studied the rotation curves of spiral galaxies and discovered something that should have been impossible. The outer edges of galaxies, the stars farthest from the galactic center, were orbiting just as fast as stars near the middle. This is not what Newtonian gravity predicts. If you spread mass outward from a central point, outer objects should orbit more slowly. But they didn't. The galaxy was spinning like a rigid disk. The explanation physicists settled on was elegant in its simplicity and devastating in its implications. There must be a massive halo of invisible matter surrounding every galaxy. Matter that doesn't interact with light in any way, doesn't emit it, doesn't absorb it, doesn't reflect it. Dark matter. And by our best calculations today, it makes up approximately 27% of everything in the universe. We have never detected it directly. Not once. Every major underground detector, LUX, Xenon 1T, Panda X, has come up empty. Every collider experiment searching for dark matter signatures has found nothing. The Large Hadron Collider at CERN, capable of probing energies at the frontier of known physics, has not produced a single confirmed dark matter particle. And that's not even the terrifying part. The terrifying part is that an alternative explanation, modified Newtonian dynamics, the idea that gravity itself works differently at large scales, has refused to die. Some astrophysicists believe we've been searching for a substance that doesn't exist, built as a placeholder to save a model that may itself be wrong. If dark matter is real, we live in a universe 70% of which is invisible to every instrument we have ever built. If it isn't real, our theory of gravity is wrong at galactic scales. Both possibilities are catastrophic. One of them is true. Number 5. The vacuum energy catastrophe. Quantum field theory is the most precisely tested scientific theory in human history. Its predictions match experimental results to more than 10 decimal places. It tells us that space is not actually empty, that the quantum vacuum seethes with virtual particles constantly flickering into and out of existence, contributing a baseline energy density to space-time itself. When physicists calculate what that vacuum energy density should be, they get a number. When astronomers measure the actual energy density driving the accelerating expansion of the universe, they get a different number. The discrepancy between those two numbers is 10 to the power of 120. That is a 1 followed by 120 zeros. Nobel laureate Steven Weinberg spent years grappling with this problem and noted that it represents a cancellation of terms so precise that it has no analog anywhere else in physics. This is not a small rounding error in a complex equation. This is the single largest discrepancy between theory and observation in the entire history of science. Physicists call it the cosmological constant problem, and some call it something more honest, the worst prediction ever made. And that's not even the terrifying part. The terrifying part is that the universe appears to be using the correct tiny value, not the catastrophically large one. Something, somewhere, is canceling out 120 orders of magnitude of vacuum energy with surgical precision. Either an undiscovered mechanism performs this cancellation, or the universe is fine-tuned to a degree that beggars comprehension, and that connects directly to number 2 in A, way that will change how you think about your own existence. Number 4. Dark energy is changing. In 1998, Saul Perlmutter at Lawrence Berkeley National Laboratory and Brian Schmidt at the Australian National University independently announced the discovery that won them the Nobel Prize. The expansion of the universe is not slowing down under gravity, as physicists had assumed. It is accelerating. Something is pushing space-time apart faster and faster, and that something, dark energy, makes up approximately 68% of everything in the universe. For over 2 decades, dark energy was modeled as a cosmological constant, a fixed, unchanging property of space-time itself, stable throughout all of cosmic history. Then, in April 2024, the Dark Energy Spectroscopic Instrument at the Kitt Peak National Observatory in Arizona released results from the largest 3-dimensional map of the universe ever constructed, covering 11 billion years of cosmic history. The data showed something that cosmologists had feared. Dark energy may not be constant. It may be weakening. If dark energy is evolving, if it is not a fixed property of the vacuum but a dynamic field that changes over time, then every prediction we have ever made about the future of the universe must be revisited. The ultimate fate of everything, every galaxy, every star, every atom, hangs on the behavior of a force we cannot see, cannot measure directly, and apparently cannot model correctly. This is also precisely the measurement that deepens the Hubble tension we described in number 9, because a changing dark energy would affect the expansion rate of the universe, differently depending on when in cosmic history you measure it. 2 crises, bleeding into one. Number 3, the universe is too smooth, and then it isn't. The cosmic microwave background, that ancient light, the relic radiation from 380,000 years after the Big Bang, is strikingly uniform. The temperature fluctuations across the entire sky are tiny, about 1 part in 100,000. This smoothness, called isotropy, is one of the foundations of the standard cosmological model. But there is a problem with how the universe got so smooth, and it is deep. In the earliest moments after the Big Bang, different regions of space were so far apart, expanding so rapidly, that they could never have been in contact with one another. Light, the fastest thing in the universe, could not have carried information between them, and yet they have the same temperature. This is called the horizon problem, and it is a genuine contradiction at the heart of the Big Bang model. The solution physicists invented, cosmic inflation, an incomprehensibly rapid expansion in the first tiny fraction of a second, predicts that inflation should leave a specific imprint on the CMB in the form of gravitational waves. As of today, that imprint has not been found. Inflation remains mathematically necessary and observationally unconfirmed. Here's where it gets disturbing. The smoothness problem and the galaxy formation problem from number 10 are connected in a way that compounds both. For the universe to be as smooth as it is, inflation had to happen. For inflation to work correctly, the conditions at the Big Bang had to be set with extraordinary precision. And yet the universe then produced galaxies too massive, too early, for the inflation-seeded density fluctuations that created our entire model of structure formation. The model depends on inflation. Inflation's predictions aren't matching what we see, and the mismatch is growing every time the James Webb Space Telescope points at the early universe. Number 2, the universe may be a simulation. In 2023, Melvin Vopson at the University of Portsmouth published a paper in Ape Advances proposing a new law of physics he called the second law of infodynamics. The argument is built on information theory. Vopson observed that in physical and biological systems, from subatomic particle behavior to the compression of genetic code in DNA, information entropy tends to decrease or stay constant over time, not increase. Decrease. This is the opposite of what thermodynamic entropy does, and it runs counter to our intuitions about a universe moving toward disorder. Vopson argues that this pattern, the universe systematically minimizing information content, is precisely what you would expect if reality were a computational simulation. Optimized for efficiency. A simulation that compresses data, removes redundancies, and runs on information rather than physical substance. He points to quantum mechanics itself as supporting evidence particles do not have definite positions or states until they are measured. Before measurement, a particle exists as a probability distribution, a superposition of all possible states simultaneously. That is not the behavior of matter. That is the behavior of a variable in a program, waiting to be read. The part that should concern you is this. The 2022 Nobel Prize in Physics was awarded to Aline Aspect, John Clauser, and Anton Zeilinger for proving, definitively, through loophole-free experiments, that quantum entanglement is real. Two particles, separated by any distance, share correlated states instantaneously. Einstein called this spooky action at a distance and rejected it. The Nobel laureates proved it is real. Instantaneous correlation across space is not physically possible in a continuous material universe. It is, however, exactly what you would expect if both particles are variables in the same computational system, accessing the same underlying data structure regardless of their apparent spatial separation. None of this is proof of simulation, but the laws of physics that govern our universe have begun, in multiple independent lines of inquiry, to look less like the rules of a physical cosmos and more like the architecture of something running on something else. And now we arrive at number one. Number one, the fine-tuning of everything. The universe runs on constants. Numbers baked into the laws of physics that determine the strength of gravity, the mass of the electron, the speed of light, the force that holds atomic nuclei together, and the cosmological constant that governs the expansion of space-time itself. These numbers didn't have to be what they are. There is no law, no deeper equation, no higher principle we have found that forces them to take specific values. They simply do. And they are not approximately right for life to exist. They are precisely, catastrophically, impossibly right. Change the strength of gravity by 1 part in 10 to the 40th power, a number so small it has no meaningful analogy in physical reality, and stars cannot form. Change the mass of the up quark by a few percent, and protons become unstable. Alter the cosmological constant by even a fraction of its observed value, a constant that already sits 120 orders of magnitude below what quantum field theory predicts, and the universe either collapses under its own gravity or flies apart so fast that no matter ever clumps together at all. No stars, no planets, no atoms heavier than hydrogen. Nothing. Steven Weinberg, Nobel laureate and one of the founders of the Standard Model of Particle Physics, calculated that the observed value of the cosmological constant is the maximum, value that would still permit galaxies to form. Any larger, and structure never emerges. The universe is not merely compatible with life, it is, at every fundamental level, set to the minimum necessary settings to allow complexity to exist. And it is set there across a dozen independent constants simultaneously. This is not a philosophical argument. This is mathematics. The probability of all these constants landing simultaneously at life permitting values by chance, under any reasonable prior distribution, approaches zero in a way that is genuinely difficult to dismiss. Here is where every thread in this video converges. The impossible early galaxies that break our timeline. The Hubble tension reveals a universe that expands at different rates depending on how you look at it. The axis of evil aligns cosmic structure with our tiny planet. The vacuum energy catastrophe, a 10,120 discrepancy, somehow canceled to allow our existence. The dark energy that appears to be changing, threatening every prediction we've ever made about the future. Quantum entanglement connects particles across any distance instantaneously. The information compression is encoded in the laws of nature themselves. Every anomaly, every crisis, every broken model points toward the same conclusion. Either we are catastrophically wrong about the fundamental nature of reality or the universe. we inhabit is not the default random outcome of unconstrained physics. It was arranged, precisely, impossibly, to a tolerance that makes randomness an untenable explanation. We don't know by what. We don't know for whom. But the evidence is no longer subtle. The universe is not what we assumed it was, and the more precisely we measure it, the stranger it becomes. If you want to see more videos like this, click the video on screen now and make sure to subscribe.